Now we will discuss that if I give you a string and you want to know if it is a formula or it's a random string, then how can we detect that? So if a formula f belongs to the set P, then it must have been generated by unfolding one of those generation rules. So this application of the generation rules or unfolding of the generation rules is called parsing. Let's suppose in string f or formula f belongs to P, then its parse tree looks like this. It has a root, which is the formula itself, and it has leaves which have atomic formulas. Okay, remember the atomic formulas, which are either P or some variable or true or false symbols. Each internode is formed by applying some formation rules on its children. Okay, so let's look at an example. Okay, so let's suppose you have this formula and you applied the formation rule, which is for implication. Then you obtain the formula from his children, which is P1 and this formula. Similarly, this formula is constructed by applying not P and this formula and obtaining this formula. You see that a string will become a formula, it must have a parse tree. How else it can belong to PP? But how do you know that particular given string has a parse tree or not? So you need a theorem. The theorem says if a formula or string belongs to P, if and only if there is a parse tree of F. If that is the case, then you have a very efficient way of checking that given string is a formula or not. Just compute its parse tree. So the reverse direction is immediate. If you have a parse tree, it clearly is because of unfolding of your generation rules, therefore it belongs to P. In the forward direction, we need to prove that if a string does not follow any given generation rules, then there is something will go wrong. You will not be able to find a parse tree. So, but what you can do is to prove something even more stronger. If a formula belongs to the P, then you can construct a parse tree, and there is a unique parse tree, and there is an algorithm to computing the parse tree. We will not prove this theorem in this lecture, and end of the slides you will find that this theorem is proven in great detail. So we have been thinking that parsing produces parse tree, okay? And the term says it's a tree, but actually it is not. And if anywhere any computer stores a formula, it does not store it as a tree. It usually stores it as a directed acyclic graph. However, the parsing produces a parse DAG. So look at this formula, and if you try to unfold it, so you will find that the right child is not P and P2, and if you break that formula again, then you get not P1 P2, not P1 can be split again, and you obtain this P1. Okay, and P1 is also a left child of the top formula. So instead of having two copies of P1, you just store one copy of P1, and then you get this DAG. And it can be a very compact representation of the formula. The large formulas are usually stored as this DAG, not as explicit strings. Otherwise, you'll be wasting too much space. Now let me introduce one more definition, which is called subformula. A formula is G is a subformula of formula F if G occurs within F. Okay? G is a proper subformula of F if G is not F. Okay, it's fairly simple. It's like very much like subset and proper subset. A sub F denotes the set of subformulas of F. Okay, the nodes of the parse tree of F form the set of subformulas of F. It's pretty clear from the definition. Okay. Immediate subformulas are the children of the formula in its parse tree. So immediate formula immediately below, not not descendants, just immediate children. We call them immediate formulas. And this definition is useful sometimes in some contexts. And leading connective is the connective that is used to join the children. The thing sitting on top is connecting things to create the node is called leading connective. So these definition terms will be appear now and then in our slides. Here's a formula. So you can see that that in this formula you have a leading connective here, and it joins these two formulas, not P2 and this guy. And again, not P2 is built from P2, and P1 and P3 is built from P1 and P3. So all these things you can see is a sub formulas of this one big formula.